Professor Alberto Sangiovanni Vincentelli.
So, repeating. So, as I said, it's a pleasure for me to talk about something I'm very passionate about, which is design. And design, it means many different things to different people. And it is a very important thing for the present day technology, but also for everybody's life. And it is a strange thing, because it's one side is an art and one side is a science. And one thing is very grounded to everybody's life, but at the same time, it has very basic principle about what it means to do research. Now, on the left, you see a piece of my quote-unquote curriculum in the sense that, yes, I am a professor, but I'm also an entrepreneur. And in my late stage of my career, I also spent quite a lot of time in the venture capital business. So I'm trying to give you some insights that I gained in my 35 years of work, which most of has been in California. So if we look at the present, we talk about the art of design. So these are wonderful example, the Calatrava Bridge in Bilbao, and you see the famous sail in Dubai. And you see, of course, the Ferrari. You know, that's one of the most incredible examples of great design. And it is a combination of beauty and also of mechanical engineering. Now, but what we are witnessing today is the fact that this way of doing design has problems. So how many of you have read about the famous sticky pedal, accelerator pedal of Toyota? I think all of you. And how many of you know that there are about 10,000 recalls per year on products that are related to automobiles? So it's not a single case. A lot of problems are in today's products, and in particular in things like in transportation, which are critical. So what about airplanes? So air-based problems, for example, the A380 was about 3 years late to market. And some of the complexities are related to the wiring, to the connection of the various subcomponents. And there are 530 kilometers of wires in a single plane. So you can imagine how many things can go wrong. I mean, I'm sure that in your homes, you see that there are several problems due to the fact that you have some faulty connection. Imagine 530 kilometers of connections. Now then, you have also followed, probably, on newspapers also in Italy about the problems that have been bugging the 787, with the Dreamliner, right? So the great plane that is supposed to be coming out very soon. Now, for example, right now, they face problems that are related to very late delivery of the product. So Air India has sued Boeing for more than $1 billion for late delivery. Not only, but during their designs, they developed test planes. And these test planes are used for several tests. But they found out that it was a basic problem. And so they had to write off all the test planes. And that is about $2.5 billion. Right? So it was almost ready to go, but boom, Boeing 787, November 25, 2010, is set back as blaze forces fix. And now that was a fire that was on a plane that was flying on a test. And so back again to the drawing board trying to eliminate these problems. So the issue is that if today we have this kind of problems and this kind of cost to bring a new product to market, imagine the products of the future. Software bugs, for example. We know that in almost all objects that we play with, you have semiconductors in it. And most of the semiconductors that you have a microprocessor in it. And most of the products that we use have software in it. So guess what? The software is buggy. We know that, many of you who are in technology and write software, you know that it's difficult to write error-free software. And in fact, in particular, for embedded products like the one that we have been talking about, software bug costs $59.5 billion per year. Okay, so the size, the economical impact of this problem is very, very large. And so, is that a situation that is so difficult that will impede us to make progress? Probably is. And in fact, when you start looking at the kind of things that are coming out down the pike, these are some wonderful architectures that have been proposed. And this one is the most fascinating of all. You see this building that looks like a dune in the desert. And the point is that to build this kind of buildings, you have a lot of technology that goes into it. And this technology is very difficult to develop and to make sure that no problems arise. Now, but you have seen nothing yet. So this is complicated things, right? Complicated buildings. They have to come out, they have to stand, possibly have to be resistant to earthquake and so on. But let's look at the information technology domain. So we are used to think in the old times, right? I'm in this field, I've been for 35 years. So I've seen the time where computing meant the big iron. So do we have the big irons? Yes, we do. It's a center of computing, if you like, where the computation goes on. At the outside is what we live today, is a mobile access. So we have smartphones, we have laptops that deliver to the masses the power of computing. But that's nothing yet. What the real revolution is coming down in the next few years is the sensories war. So it's an environment where everything has an electronic content, so that you are completely connected all the time with all kinds of devices. And some of these devices are transparent to you. So in some sense, the sensories war is creating a Copernican revolution in which instead of being the device, the center of your attention, is actually you. So you control the environment because the environment recognizes you, sees you, reacts to your desires. Okay? Now, is that the only thing that you can do? But you can imagine of having a device right here while I'm walking around, and I don't need to have all this stuff, all these wires hanging out of me, because I have microphones that are tiny microphones in my tie, hidden. And I can say it like this, and the microphones come up. And these microphones connect to wirelessly to the environment so that you can hear my speech with no need of funny amplification devices and the like. Think also about the health implication of this. Imagine that one of us has a problem with a heart disease, and it has to be under control. So already today, I'm a runner, so I have this kind of weird stuff that you put around the chest to figure out if your heart is going too fast and the like. And now, this particular device can be always attached to us. It can always tell us if our heart is going well or not, without all these horrible things that you have to wear. So, prediction. So, 5 billion people are going to be connected by 2015. There is an emergence of Web 2.0, which is the always connected community network. It is predicted that 7 trillion wireless devices are going to be available in the next 10 years, which means there's 1,000 devices per person. Okay, so what do you do with that kind of stuff, right? Is the birth of societal IT systems. Is the fact that, as my predecessor was speaking about, is the importance of society. So technology not only serves you, but serves society. So you can imagine that these devices can be used to minimize the effect of an earthquake. It can optimize the use of health devices, can optimize traffic, can do anything, right? So the world is going to be fundamentally different in the future. But what is going to provide us, right, with this computing power, which is behind all these devices? The cloud, right? We have heard a lot about the cloud. And the cloud is just saying that there is an infinite compute power available to you, but it's hidden from you. It's somewhere, and we don't know where this computing power is. Now, this one is an incredible business opportunity. So not necessarily to be good for society implies that you don't have to think about money. The two things can go together. The vector have to be aligned. That is the important factor. You don't want that the financial aspect go orthogonal to the interest of society, as sometimes have. You want them to align. And so the issue is about that. So the cloud is one way of providing infinite business opportunity that are enabled by the sensory swarm that we said before. Now, this is a famous GM slide. So one of the things that we are really investing a lot in General Motors, as well as in other automotive companies, is to develop a refuse-to-collide car, which means a complete safe car. Now, if you look at what are the issues when you drive a car, is the driver, right? Is the driver that it gets drunk? Is the driver that falls asleep? Is the driver that wants to be smarter than the next guy and cuts over, right? Is the driver. So what is the problem with the car? Is the driver. So we want to eliminate the driver. So short to kill him is that we want the car to drive by itself, right? And so how do you make the car drive by itself? You want to give it eyes and ears and hands and feet and so on, right? So this is it. And it is possible. Why? Because of a sensory swarm, right? And so in fact, the next generation car is going to be full of radars, right? All over the place, so that you can see what is around. And you want to have control systems that regulate the behavior of the car in such a way that you never have the opportunity to have an accident. Okay, fantastic. Let's look at another thing. Right now, how many of you have seen your children asking, "Dad, can I have a glass of water, please?" Say, "Go and get it," right? And, "No, I can't, I'm so tired." Okay, so imagine that your kid has a brain in which there is an implanted device, right? There's a computer in his brain. And he thinks, "I want the glass of water." And all of a sudden, the glass of water comes to him. Isn't that wonderful? It is possible. Now, this is called the brain-machine interface. So you can connect directly the brain to this wonderful information technology world that you have around you, and you can control the environment. Now, that, of course, is a folkloristic aspect of it. But you can imagine how many people have impairment, right, because of brain disease or because they have had an accident for the cars, famous cars, and these kind of devices can allow them to live a normal life. And so this interconnection between the virtual world and the real world is a key component of future society. So now, what is the problem with all of this? Well, you have 7 trillion devices that you want to connect. Already today, I think that all of you, once in a while, have a problem with your laptop, your cell phones, and sometimes you get weird connection, you know, sometimes the Poste Italiana, I understand, went down for a week, right? And everybody was, "Oh, how do we send stuff?" and so on and so forth. So connectivity is a great thing, but is also making our life fragile, because the more you connect, the more fragile you are. Not only, but the more amenable to bad guys coming in, right? It's not as safe as before. And so in general, if you hear the old talks about Microsoft, they were saying, well, gee, the future is plug and play, right? But what it is today is more like plug and pray, right? So let's hope that everything goes, right? Well, how about the design problem? So the design integration nightmare comes from a simple fact. It's the fact that you have in mind an idea, and design is about realizing that idea. So you have to dream something, but you have to realize it, right? And so then you have to say what your specifications are. So it turns out that I am a great fan of Picasso. So let's use Picasso to drive home this point. So suppose that this is your specification, this wonderful painting here, right? Okay, so then you go and you try to implement that vision. And what you get is, again, Picasso, but it is a woman, right? So it resembles what the specification was, but is not exactly what you had in mind. And this is the issue. Design is the key to prevent this from happening, right? And so you want to make absolutely sure that your design process is delivering what you had in mind. Now, one problem is the fact that when you realize things, you miss some of the important points. The other problem, especially when you have 7 trillion devices, is what is called emerging behavior. And the emerging behavior is things that occur because of interaction among objects, also among people, by the way, that you didn't think they were possible. So there are side effects, call it, that you didn't think could be possible, hence you didn't design against them, right? And so this is a very, very serious problem, emerging behavior in design. So, but we have gone a long way. So once upon a time, there was the Moore's law. Now, I think that many of you may not know about semiconductors, but I'm sure that at least some of you know about semiconductors. And we say before that semiconductors are the heart and the minds of most of the system of today. Now, when I started my adventure in California, the largest semiconductor that we were able to design was about 20 transistors. Okay? Now, don't laugh. That was difficult, I guarantee you. Now, you know how many we designed? 10 billion! 10 billion transistors, right? The latest chip from Intel is 10 billion transistors. So from 20 to 10 billion, right? So how was that possible? How did we conquer this complexity? And that is going to drive home my point that we need to really focus on design. So, well, yours truly in 1984. So this is me, right? And it doesn't look like me, but it is me, okay? With 2 guys from Intel, Gene Hill and Pat Gelsinger. He was in charge of the design of the 386. He was the chief architect. And so, well, Intel bet on some of the stuff that I was doing at the university and say, well, this is the only hope for us to deliver the processor in time. So Intel has a bit of 2 years. Every 2 years they have to come up with a new device. And so they say, we're never going to be able to do it unless we do design as a science. So we have to use new methods. And so happens, as we say before, that my interest in science was very much tied to design. Okay? And so I developed some technologies, and they say, well, this looks interesting, so we went on and did it. So, well, after we did that, they came to me that we could form companies that do this kind of stuff that we were developing at the university. But it was not my main goal. My main goal, and in fact, some of you may remember that Berkeley is called the Free Republic of Berkeley, or Berkeley, okay? So any right-wing president or governor think that Berkeley is full of communists that hate, you know, money and all of that. Well, it's in part true, right? So in fact, our friends did not make the example of Berkeley. Thank you. Because we don't think of money first. The key point, but I mean, this is a joke, right? So, the point is that for many people, also in the United States, what matters is impact. To have impact. And this is the same thing as the Renaissance in Italy. It's to have impact. You know, why do you live? Because you want to leave a sign. You have been alive and you have done something that people will remember you for. Possibly in good terms, right? Not because you have been, you know, a famous serial killer that has killed 20 people. No, no, not that, okay? So the point was that, yes, forming the companies was a way of making sure that what you did had an impact. So much so that my colleague Richard Newton and myself never left the university, okay? We stayed with the university. That was our life. That was our mission, is to inspire young students, is to do new things, right? And so we got together with some people in industry and we formed these companies. Now, we started 7 people in a Chinese restaurant in Berkeley. 7, okay? Now, the combination of the 2 companies that we formed is more than 11,000 people, and their market capitalization on the stock market is more than $7 billion. I mean, at the top, before the big crisis and so on, was like 12 billion, but you know, that's still okay. I don't complain about the 7 billion stuff. But is that the important thing? No, it's not. It's the fact that we have made it possible to design 10 billion transistor systems. And without this, you will not have had the Apple iPhone and the TV and the cars and all this kind of stuff, right? That is the impact, right? And the impact is about the method that you use for designing this. So part of my title was about transcendence and immanence, right? Is this tension, right, between the science, between what is under the problem and the fact that you want to get, after you have delivered that vision, that understanding what the problem is, you have to want to have an impact. So you have to be immanent in the work. So this one is the, I know that many of you know, but it's the Athens school. So you see Plato, that is pointing to the transcendence, and Aristotle is, say, immanence, right? So being rooted in the physical world. So how was this all possible? How come that from research we were able to form companies, and these companies had such success? Silicon Valley, the land of innovation. It's always 18. Oops, 18. I thought that I had 18 minutes. Sorry. Okay, so Silicon Valley, land of innovation, that is possible. There are all kinds of interesting phenomena. But if you want to know why the Silicon Valley is so interesting, because it's an ecosystem. It's not because of any single thing. It's because many things come together. And this comes with transcendence and immanence is the interest of quest for fundamental understanding and user-inspired based research. So this is what is all about of the universities in United States. It's combining the user-inspired motion, but with the quest of fundamental understanding. So this one is actually the map of where innovation can be measured in the United States, and you see that the number of patents, the most referenced patents, Silicon Valley, you see how tall it is with respect to the rest of the United States, and you see next is Boston, but the difference is huge, right? And notice that all these peaks are all related to where the most important universities in the United States are. There is not a single place where there is no major university, okay? So this is also a very important lesson for Italy, I guess. Okay, so, well, money follows this. And in fact, most of the money from venture capital goes to California. There is a consequence between where the value is and where the money goes, okay? So, from art to science, for our general principle about design, which is based on abstraction and is based on divided impera, so decomposition of the problems. But last message I want to give you is that you have seen yet nothing. And the nothing is about synthetic biology. So not only we are creating new devices, but we are creating new living organisms. Frankensteins, right? Not exactly, so small microbic elements, but we can go to BioShack and buy components for biological items and build new living organisms, right? And so, and you can do energy crop, biodiesel, biojet fuel, natural product drugs, and so on. Companies, as usual, this is Berkeley. Of course, I know Berkeley best. So this one is a company was born from that research, but was born in Berkeley. This is called Amiris, and the key patent was in 2001, and today went public in the fourth quarter 2010, from 680 million cap to 1.2 billion in 2 months. Okay, so that's the kind of potential that you have with new revolutionary ideas. And so the question here is that we have an educational challenge to create people that can do that kind of innovation. And we have a long history about being capable of doing this, right? Leonardo, there you go. That's my last slide. Thank you very much. vedo il chat, ti faccio un saluto.